All right. Hi, everyone. My name is Jack Baker, and I am going to be talking about video game hacking. So, my sort of introduction to computers and programming and hacking was through video games. I started programming little video games as a teenager, and that turned into trying to hack video games. And that sort of turned into my career a little bit later in life. And so, when I got into sort of the corporate world of doing cybersecurity, pen testing, reverse engineering sort of stuff, I noticed that there were a lot of tools and techniques that I had learned as a game hacker that really weren't all that common in the more corporate reverse engineering and bug hunting world. So this is sort of my attempt to take those techniques, take those things that I already knew how to do, and adapt them to this different world with its own techniques, its own tools, and stuff like that. So, with that being said, let's get into the first sort of lesson that I learned as a game hacker, and this is sort of how to find a needle in a haystack. So, if you have done any video game development or any video game reverse engineering, or really just downloaded a video game, you've probably noticed that video games are really big pieces of software. And of course, part of this is just that they come with all this extra stuff. There's 3D models, there's textures, there's art, there's music, all this stuff. But it's also because video games have a lot in them, and a video game engine has a lot of different parts going on. They're very complicated systems. So if we were to think of a video game engine as this really crappy block art, I'm sorry, I'm not an artist. The part that's probably relevant to us as a game hacker is really just the component of the game engine that is relevant to gameplay. But there's all this other stuff in there. There's the rendering engine that is responsible for the actual visuals. There's audio, there's input, there's all sorts of different things that are important and need to be there, but aren't really relevant when you're trying to hack a game. They're not what you're looking for. And even if we were to take the gameplay section of code and look at just that, even that is a big world in and of itself, with things like, the physics engine, the artificial intelligence, all these things that, again, are pretty big components of software and are very important, but aren't really what we're looking at for the most part. And if we were to drill down to maybe just like the parts of code that are related to our player, to the actions that we are performing, even that is, a reasonable amount of code. And the actual stuff that might be relevant to our purpose is just this tiny little dot in this big system that is the game engine and the actual game software. So this is a really relatable problem if you've been doing, reverse engineering, because a lot of times you run into these big code bases where you don't really care about everything. You're not trying to do a full, 100% reverse engineering something back to source. You're just maybe you're looking for bugs, or you're looking for specific capabilities and how they work. So in game hacking, there is this technique that is very common for basically isolating just the code that we're looking for a particular purpose. And this technique is sort of what you'll see in like a lot of game hacking 101 tutorials. And so there are a lot of names for this technique, but I like to call it differential searching. And so this technique was basically pioneered by a tool called Cheat Engine. Cheat Engine's been around for a long time. It's still very frequently used, and it's arguably the most like influential game hacking tool. It's very useful, does a lot of cool things, and we're going to talk about probably the most common one that you use Cheat Engine for. So differential searching is basically consists of snapshotting a process's memory repeatedly and repeatedly searching that memory for some sort of differential. So basically looking for values that have increased since our last search, or have decreased, or have changed in some way, or haven't changed at all. And so I'm going to give an example of how this works and how we can use differential searching to go from basically a black box. We don't know anything about the software. We're not opening it up in a disassembler, decompiler, or anything. And we're going to, with some relatively simple techniques, find the code that is specifically relevant to a value of our choosing. So in this case, we're playing our game, and our goal is basically to manipulate our health. So this is real sort of game hacking 101 stuff. We're going to try to do like an infinite health hack. And so we're here. We know that our character's health is 5. We've got the 5 hearts. So the first thing we're going to do is we're going to search the game's memory for the value of 5. It's going to come back with all the memory addresses that have the value 5 in them currently. And this is going to be a lot. We're going to have to narrow this down a lot, but we can be reasonably confident that one of these values has the value of our health in it. And so the next thing we're going to do to narrow this down is we're going to cause our value to change. We're going to take damage, and now we know our health value is 4. And we're going to search again, and we're basically going to say, okay, of all those values from the last search, of all those that used to be 5, which one of those are now 4? And that's going to narrow it down some more. And we're going to basically continue this iterative process until we found our health value in memory. And we're gonna get rid of the irrelevant stuff. We're gonna be reasonably confident that this one particular value has our health value in it. And so as a game hacker, this might be sort of where you stop. You have what you want because you can manipulate this value. We can now set it to 100 or something and give ourselves a whole bunch of health. But what we want to do in this case is we want to turn this, relevant memory value into code. We want to know what code actually is responsible for acting on this memory value, because what we want is basically to be able to start our reverse engineering somewhere. And we know the value, we know the memory address that's relevant. Now we want to know the code that is responsible for acting on this memory address. And so to do this, we're going to use watch points. If you're not familiar with the term watch point, it's basically a breakpoint that is set, that is triggered when a memory address is either read from or written to. In this case, we're going to do written to. So we're going to set our watch point on our memory address that we know contains our health. We're going to trigger this watch point by taking damage again. We're going to cause that value to change. And we're going to, the watch point is basically going to show us the exact instructions that were responsible for causing that value to change. So just like that, without too much work, without too much thought, we were able to go from sort of a black box, don't know anything about the internals of the game, and find the specific instructions that were responsible for updating our health value. And that becomes the start of our reverse engineering process. So this technique is really useful, but what you might have noticed is that we had a little bit of help because we knew exactly the starting value we were looking for. We knew that our health was 5, but this isn't always the case. It could be that it's a value we don't know the specific value of. It could also be that we just don't know the representation of it. It could be integer 5. It could be floating point 5. It could be some other representation we're not thinking of. So the question is, how does differential searching work if we're not lucky enough to know the exact value that we're looking for? And so I'm going to use another example here. And in this case, we're doing basically the same thing, but instead of looking for our health value, which we know, we're going to look for our coordinates, the X and Y coordinates of our players. So since this is a 2D game, we can be reasonably confident that our coordinates are going to be represented as an X and a Y, but we don't know exactly how they're represented. They could be a float, they could be an integer, they could be something else. We don't really know. But we do know that we can affect this value. So we can be reasonably confident that if we move to the right, our X coordinate's probably going to go up. If we move to the left, it's probably going to go down. And so we can do differential searching without a known start value. It takes a little bit longer, but the process is essentially to just take a snapshot of memory and compare which values have changed or not changed. So we can say, move to the right and ask which values have increased, move to the left, which values have decreased. We can stay in one place and say, well, which values didn't change? And in doing that, we can sort of eliminate sort of the irrelevant stuff that is changing, independent of our actions. And so in doing this, it takes a little bit longer than our first example, but we can basically narrow down, the entirety of process memory to those relevant values without too much work. And once we have those, we can do the exact same process. We can find the code that is responsible for acting on those values, and that becomes the starting point of our reverse engineering. So when you're doing differential searching, it only really requires one of two things. The first could be the ability to trigger a value change. So when we move, we know that we are changing the value in some way. Or It could be a value that just changes often and we can observe that change. So I don't know if the game has a timer and you want to give yourself more time, that's not it's something you can really trigger the change on. It's already changing on its own, but you do know that it's changing and you're able to observe that change. And that could be all that you need in order to do this differential search, because you can then say this value has changed, it's decreased or whatever, or at this point in time, this value hasn't changed, because you're able to observe when a change occurs. And so differential searching is really useful, and it can be applied to basically anywhere that you have one of these requirements. And this has been very useful for me for dealing with large code bases where it just doesn't seem reasonable to start reverse engineering sort of blind and just look through all the irrelevant code until I find the relevant stuff. This is a really simple and kind of maybe a little tedious, but much quicker way of narrowing down a big code base to just the relevant parts. Okay, so the next lesson I want to talk about is sort of cheating while being watched. So let's talk about anti-cheat systems. So as the name obviously suggests, anti-cheat is software that's set up to catch and prevent cheaters. But specifically what we're talking about here is the software that runs client side on your computer, basically watching you play the game to make sure that you're not cheating. And so typically this is shipped as like a separate piece of software that's bundled with a game. So rather than being actually built into the game itself, it's a separate executable or separate kernel module or something that is bundled with the game and is sort of watching the game as it goes. When I'm talking about anti-cheats, I really want to talk about like modern anti-cheat systems, because there have been a lot of anti-cheat systems over the years. But I really want to talk about the complicated, really really modern ones. So these are things like BattlEye, Vanguard, Easy Anti-Cheat, things that are used in the bigger games and have a lot of work put into making them resilient. Modern anti-cheats typically have a few things in common. At this point, they typically run partially or fully within the kernel. They do signature detection where they look for known executables or known patterns of cheats that have been seen before. And they do heuristic detection where they basically just look at the behavior of processes and flag if they see something suspicious. And anti-cheats typically will detect and stop most of the common process modification and process injection techniques. So if you've got an anti-cheat running on a game, you probably can't attach a debugger to it. You probably can't just write process memory or inject a thread into that process, because that's sort of what anti-cheat is there to stop. Those are the things that it's really good at stopping. And if you want some extra reading about sort of the technical details of anti-cheats, this is a great write-up on BattlEye. This is not mine, but it's a really good write-up. And so if you looked at that list of things that anti-cheats are doing, you probably may have seen some parallels with like antivirus. And yeah, the parallels there are fairly obvious. But there is one big difference between like anti-cheats and antiviruses that I think is almost like philosophical in a way, and that antiviruses ostensibly are there to help you. You're not the enemy in antivirus. Antivirus is there to protect you from a malicious third party. But when you talk about anti-cheats, the user, you who owns the computer it's running on, are sort of are the enemy. Anti-cheat is there to prevent you, who has physical access to the computer, from doing something that you may fully intend to do. So it's a much more adversarial relationship with the user. And so because of this sort of adversarial relationship, anti-cheats tend to be a little bit more aggressive than antiviruses are. And they'll do stuff that you may associate more with malware than with like antivirus. So anti-cheats are typically obfuscated. They're not, something you can easily open up in a decompiler. They may even do a little bit of like cloaking to keep themselves from being seen by the operating system or by the user. And anti-cheats often will even include something like virtualization detection. So they'll check if they're in a VM, and if so, they just won't run. They won't let the game run. Stuff that you don't really see outside of like malware, and that's because anti-cheats sort of have this adversarial relationship with the users. In a way, they are sort of acting like malware, in that they are sort of at odds with what the user wants to do with their computer. Um, and so because anti-cheats are sort of adversarial, they're running in the kernel, they're doing all sorts of complicated stuff. There's a lot that can go wrong. And so anti-cheats have earned some bad headlines over the years. So this could be a much longer list. I picked out some of my favorite headlines here, but one that I love is you might remember this story a few years ago of a driver that was built into Street Fighter V, or came with Street Fighter V, that basically opened up an I/O control that anybody on the operating system could call, and it basically just asked it, hey, run this code in the kernel for me. And this driver was set up to just put that code in memory, turn off the protections that would prevent exactly this, run that code, and then turn everything back on. And so this was discovered by a reverse engineer who goes by Slipstream. I've got his Twitter account here. And this was a really fun example of an anti-cheat basically opening up the system to all sorts of security issues, just so that hypothetically someone might not cheat at Street Fighter. um, Another example I really like is the case of De Novo Anti-Cheat, which was doing things that were suspicious enough looking that some antiviruses were doing heuristic detection and thinking, wow, this doesn't look right. This looks like malware to me, basically flagging the anti-cheat and making the game unplayable for users because they couldn't run the game because they couldn't start the anti-cheat. And of course, there are always dozens of examples of anti-cheats screwing up and doing something like crashing somebody's computer or banning a bunch of people who weren't actually cheating. All good stuff, all hallmarks of software that you want running on your computer, obviously. Um, and so before we talk about sort of bypassing anti-cheat, I think it's important to understand what is it that anti-cheat is preventing us from doing that we want to actually do. So this could be a longer list, but the common stuff that your cheat might be doing that anti-cheat is trying to stop could be stuff like reading from process memory to see information that isn't directly exposed to you, writing to process memory in order to do something you wouldn't be able to do, injecting new code or threads into a game, or just like hooking library functions or syscalls of the operating system in order to sort of manipulate how the game runs without actually touching the process. And so these are all things that anti-cheat is probably looking for, and that it might be preventing you from doing. And that is why we need to bypass it, so that we can do these things. So when we talk about bypassing anti-cheats, one of the things that has become more common is basically moving cheats into the kernel. So if anti-cheat is moved into the kernel, it only makes sense that cheats need to do the same thing and do the cheating from kernel level. And what this allows those cheats to do is basically poke and prod at the game process without having to do sort of the user mode level, like process injection sort of stuff, because user mode process injection is a little bit easier to catch, particularly if it's a known method. It's something that a kernel level anti-cheat is going to be pretty good at catching. So moving into the kernel gives cheats the opportunity to sort of bypass that whole difficult part. The problem with this is that anti-cheats get really suspicious if you're running unsigned kernel drivers. In fact, a lot of anti-cheats, basically, they won't start and they won't let the game start if they notice that your kernel is running a module that's unsigned. And since your cheat is probably not signed by a legitimate certificate authority, this can be a little bit of a challenge. So dealing with this problem, there's a few solutions that you see pretty commonly. The first is like leveraging bugs in legitimate signed drivers. So if we were to go back to that Capcom driver, the Street Fighter V one that opens up your kernel to anyone on the system, this was a driver that was, of course, created as part of an anti-cheat, but it actually gave birth to a whole bunch of cheating tools that used this legitimate driver that was signed by a legitimate authority and was excuse me, trusted by the operating system, and they used it to write the game hacking code into memory and basically let you bypass these anti-cheat protections using a legitimate driver. So this particular driver doesn't really work for this anymore because the Capcom.sys has basically been blacklisted across the board for good reasons. But you'll see this technique very common with other legitimate drivers that have some sort of, vulnerability or bug or unintended functionality where you can write code into kernel memory and use that as basically the loader for your cheat. Now, if you want to throw money at the problem, you can also just sign your own driver. You can fill out the paperwork, get a code signing certificate, sign your driver, and have it sort of be a little bit more hidden from anti-cheats. Now, this doesn't really scale well. Like if you're trying to do this with a tool that you think a lot of people are going to use, your signature, your signing key is going to get blacklisted pretty quickly. But if you're just building your own tool, this is a pretty simple way to sort of solve the problem with money. I think this is a little bit boring because I think actually going through the process of bypassing anti-cheat, that's part of the fun. That's part of the difficulty there. But if you don't care about that, getting your own signing certificate, using it on your own kernel driver is a reasonable way to deal with anti-cheat sort of through the official channels. And then, of course, there's always a world of just sort of anti-cheat specific bypasses. So this could be something like putting your code somewhere that anti-cheat isn't looking for it, or having some method of process injection that it doesn't know about. Or it could just be like finding some way to stop the anti-cheat from doing what it's intended to do. And this is sort of the cat and mouse game of, method is found, method gets fixed, stuff like that. But there is this whole world of bypassing anti-cheats by looking for specific, flaws or deficiencies in its ability to detect what you're doing. So something that I really like is cheats that are physically or logically separated from the system that's actually running the game. So since your anti-cheat is running client side, it's on the computer that is running the game. If you can sort of separate your cheat from that computer, this is a really effective way to not get caught. And so for an example, many cheats, there are cheats that you can pull off basically just by listening to the network. So if let's say you're playing a battle royale, let's say, in fact, this was common in PUBG. There's a lot of information that is given to your client that isn't exposed to you, the player. So your game client knows about player locations that it's not actually showing you because you can't see that far or you're not looking in the right direction or whatever. But the client needs to know it's there because it needs to be able to load resources before that character gets into range. It needs to be able to make sounds if they're doing gunshots, a mile away or something like that. So your client has more information than it's giving you. And that information is provided from the server, obviously over the network. So if you're able to just listen to the network and pick out that important information, off the wire, you can build basically an undetectable cheat by basically man-in-the-middling yourself, listening to traffic, and just picking out the stuff you want. You're not interacting with traffic. There's no, noticeable change to the server or even the client. And you're not cheating on your local system. So this is a pretty hard to catch way of cheating without interaction. Now, this method does get a little bit more difficult once you apply some sort of like encryption layer to that game traffic. So this kind of attack, this what we call radar hacks, was really common in PUBG for a while before they added an encryption layer to the traffic. And so this gets more difficult because while your client obviously has the ability to decrypt that traffic, otherwise it wouldn't be able to read it. Um, that decryption key is somewhere in the process. It's probably created in a way that you can't just guess it or something like that. And so you get back to the same point of, well, I need to read process memory, or I need to manipulate in some way so that I can get that key out and hand it off to my radar hacking tool. So this is sort of a cat and mouse game too, but these kind of hacks are still pretty common, and they're really useful and in my mind really clever when they work. Another example of sort of a logically separated cheat are cheats that basically separate themselves by appearing as a peripheral device. So when I was a teenager, I played an MMORPG and I really did not have the patience for it. So I bought this little like botting tool, and it came to me shipped as this tiny little, like, it looked like a USB stick. But it blew my mind because I would plug it in thinking, it would open up like a flash drive, and instead it would just start playing the game for you. And so I wasn't much of a reverse engineer, wasn't much of a program at the time, but I was so curious about how does this thing work? It's so interesting that I did a little research, and I figured out that when you plug this thing in, the computer doesn't see it as a flash drive. It sees it as a USB hub that's connected to a keyboard and a display device. And so assumably what the thing does is it just sort of reads the screen and types on a fake keyboard, kind of like you do, just looking at what is on the display and typing. And so this was really, really difficult to catch because there's not really anything there for an anti-cheat or for any protection to see. It just looks like a keyboard. It just looks like a display. It just looks like someone playing the game. And so this was kind of mind blowing to me. And I wish that I still had this device because I would love to have done like a full teardown now that I have a little bit better of an idea of what I'm doing. But this always stuck with me of such a clever way to bypass those client level protections just by behaving in a way that looked as realistically as possible like a real user. So when we talk about bypassing anti-cheats, this has been, a really short list. There's a lot of ways you can do that. There's a lot of clever methods, but I just want to give sort of an overview and say that like a lot of these techniques that are used to bypass anti-cheats can be used to bypass antivirus or other security controls, things that you might deal with in like the regular corporate sort of day-to-day cybersecurity. And in fact, I would say that a lot of these techniques tend to be overkill for that kind of thing because antivirus isn't as aggressive as anti-cheats. You just don't need to go to this extent. But it's always nice to know that there are these really, intense methods, and there are game hackers out there building these really, sort of revolutionary bypass methods to deal with anti-cheats, and that they can be adapted whenever you need to bypassing, Kaspersky antivirus or something like that. And conversely, if you are a reverse engineer, there's a lot you can learn about sort of malware analysis by looking at anti-cheats because they do a lot of the same stuff. They are very, adversarial software to the user, and they have, a lot of funding and a lot of support behind them. So there's a lot that can be learned that you can apply to, regular reverse engineering that comes from looking at anti-cheats and looking at software that is built to stop hackers, game hackers, that is. Okay, so the last lesson I want to talk about is about emulation. And so game hackers obviously did not invent emulation. Emulation has been a thing for a long time, but it is definitely true that when we hear the word emulation, we tend to associate it with something like playing N64 games on your laptop because emulation is so common in the context of video games, and so much work goes into emulating video games. And so, as someone who has done a lot of embedded reverse engineering professionally, video game emulation has actually been a kind of a gold mine for me. So I'm going to tell a bit of a story here. But at work, I at one point was dealing with software that was written for a particular digital signal processor. Excuse me. And this digital signal processor was built in the early 90s. It wasn't really a long running model. It's not totally obscure, but it's not something really common either. And I just didn't feel like I was going to find an emulator for it. So I did, typical looking. I looked on GitHub, looked on Google, didn't really find anything, and sort of gave up on the possibility that I was going to find an emulator for this processor. And then, I don't know, a few days later, I just by pure coincidence, I was working at home on building one of those like arcade machine emulator tables. And I had this little Raspberry Pi. I was building MAME, the multi-arcade machine emulator, on this Raspberry Pi so that I could, emulate games on it. And I see a really familiar term scroll by in the GCC logs, and I realized that's the name of the digital signal processor that I was working on at work. And so immediately I go into the MAME source, I look at it, and I realize there's a full-featured emulator for this kind of rare digital signal processor built into MAME, just so that someone can emulate the sound card of an arcade game from the early 90s. And so this sort of blew my mind because I was like, oh my gosh, I never thought to look at MAME as something to be using for embedded emulation and embedded research outside of video games. Normally, if I wanted to emulate something, I'd look at a QEMU, and if it didn't work, which it pretty often didn't, I'd be like, oh gosh, I guess I'm out of luck. But so I decided to do a little bit of like a comparison. And so if you look at like the QEMU wiki, it'll say that, it supports something like 22 architectures. I don't know if that's completely up to date, but it's somewhere in that range. And that's a lot. Like there's a lot of work that goes into that amount, supporting that many architectures. And there's, a few dozen CPU supported per architecture. There's a lot of code coverage there. But conversely, MAME supports over 100 architectures. And in fact, depending on how you choose to count it, it could potentially even be closer to 200 if you want to be liberal about it. And like a countless amount of different specific boards and CPUs and stuff like that. And so specifically, if you're looking at like digital signal processors, you'll see a lot of that in MAME because you have to do, if you're emulating an arcade game, you have to emulate its sound card, you have to emulate its graphics processor, you have to do all of that stuff. And that tends to have some more obscure systems, more obscure architectures on there. So MAME has sort of become like my go-to when I've been trying to emulate some sort of more obscure software that isn't x86. It's not ARM. It's not the stuff that's really common. I have had really good luck with MAME. And in fact, in the places where I didn't just have like a plug and play tool with MAME, maybe I had partial support, or oh, this family is supported, but not this particular processor or something like that. I have had really good luck mocking up hardware within MAME. The APIs are really easy to use. The code is pretty self-explanatory, and everything just sort of works pretty well. So I have had really good experiences with MAME, and it has been a huge help as someone who does a lot of embedded reverse engineering and would love to have an emulator when possible. So if that sounds like something you do, if you're doing emulation, I would highly recommend you take a look at MAME and put it in your arsenal of potential places you should look for existing code, for code you can leverage, because it is really remarkable how much code is there and how useful it can be. Those are sort of the three big things that I feel like I've gotten out of game hacking. But if you are, if you're doing this kind of work, you're doing the corporate level reverse engineering, I highly recommend you go ahead and you give game hacking a try because there's a lot you can learn from it. I mean, the fact is game hacking combines so many of the like complicated problems in InfoSec. There's, dealing with big code bases and big reverse engineering projects and dealing with code that doesn't have symbols, or it may even be like obfuscated or adversarial in some way. There's a lot of practice that goes into this. If you're a malware analyst, you're a bug hunter or whatever, there's a lot you can learn just from game hacking and going up against these systems, whether it's anti-cheat or just a big game binary or anything like that. And I would also say that game hacking is fun in that it's flashy, it's satisfying. If you're, a pen tester, it's a good feeling when you get domain admin, but you talk to someone who doesn't, who isn't a pen tester, they're not really impressed. They don't really know what getting domain admin means, but you hack some video game and it's flashy, it looks cool, people are impressed. It's fun for the senses. And I mean, if you're like me, you're getting a little bit older, you're feeling your reflexes get a little bit worse, you're not as good at video games as you were anymore. Video game hacking is a good way to, cling to that lie that you're not getting old. I'm still good at video games. Who cares if I have to cheat at them? And it's fun. You can make some 14-year-olds cry, and really that's what we're here for, right? That's the reason we all became hackers, is we want to ruin someone else's time for a little bit of dopamine hit for ourselves. So I hope that if you get anything out of this, maybe you get something you can use for your own, using your day job, using your real life work that you're actually getting paid for. But maybe you'll pick this up and realize, hey, game hacking sounds kind of fun. I'm gonna take this and I'm gonna make some Fortnite kids cry, because that sounds like a good time to me. So hopefully we'll see you online. We'll get banned from something together. But other than that, I hope you all have a great rest of your day. I hope you enjoy LayerOne, and thank you very much.